All right. So we started talking last class about drag, and really we're looking at external flow. And to be honest, the most important thing is drag. Okay? Drag defines everything from the way a water droplet falls into the atmosphere. It forms a teardrop shape. That's because of drag. Okay? Um, there's really two types of drag that combine to get an overall drag. Surface drag, which deals more with flow being parallel to the surface and going over a surface like this, where you have pressure drag, which means you have a big frontal area like this pushing here, right, and you have very little surface drag. Okay? And they're combined to get this overall drag equation, which is right here, which is 1/2 rho v squared cv times a. All right. And in a minute here, I'm going to talk about how to find CD, just the table values, and some other equations that we can use. Okay. So that is the fundamental equation for drag if you have high Reynolds numbers. Okay. And the Reynolds number was given by rho VL over mu. And we did briefly talk about if you have low Reynolds number, meaning your viscous forces are greater than your inertia. Okay, so if you have a really heavy fluid like oil or honey, that drag is going to be used by that because it's based on Reynolds. Okay, it's crazy how Reynolds number is used everywhere, and it's a very, very important non-dimensional number. So we talked about drag. We also talked about this stuff over here. We kind of did a side note, right? Which is good because it's still external drag. You have, say, any ball or any object falling in space. It's going straight down. We know that there's drag going in the opposite direction. We know there's weight force. We also know there's a buoyancy force, but we neglect that. Okay? So, in order to find velocity or position or even acceleration of that block or object falling, you have to use Newton's second law to get to that differential equation. Okay, so any differential equation is derived from Newton's second law. Okay, so another very important fundamental thing that you always use is Newton's second law. You use it everywhere, right? Dynamics. You use it in thermo to find the pressure inside a piston cylinder. You use it in almost every other class. Okay. So I think your last question on your homework, I want you to solve that numerically. And I will post a video on how to do that. I think I already have it. If not, I'll make one to help you. Okay? And then watch that video kind of side by side. Okay? Because once you do it once, then you can do any other differential equations the same way. Okay? But I'll see if I can find that video. If not, I will make one for you to help with that homework. Okay. So just again, refresh. What kind of can you classify that differential equation for me? First order, non-homogeneous, it's nonlinear, and it's constant coefficients. Okay. That all means you just go ahead and you can go to the math book and figure out how to solve it. But in this case, nonlinear problems, because v is squared, are very tricky to solve. Okay, so we use a numerical method where we guess values as you go on. And this method I'm going to show you is pretty reliable. I mean, it actually works pretty close to get the exact solution. Okay. And what is a differential equation? Some sort of equation that will provide what? A function. Yes, who said that? Yeah, a function, meaning velocity as a function of time. Okay. How can we write velocity in terms of position? Second derivative, right? Yep. So a differential equation has a function well, it doesn't always have to have a variable, but it has to have some sort of linear, like differential equation, like differential, like d dt or d squared x dt squared. Do you know why it's written like that with the 2 after the d, and then the 2 after the t in the bottom? Because you're taking the derivative of dx dt. Okay? That's what that means. All right? Where dx dt is v. Okay? You see how that's why you write it like that? I don't know if you've ever been taught that way, but that's how it was. Okay. So there's that differential equation. I'll make a video on that. We did some stuff on terminal velocity, but that's fine. We talked about that. Talked about lift and drag. Okay. Talk about boundary layer. All right. So if you have any object, you have flow going over it. Okay? It could be in an airplane, it could be a car, whatever. The front part, okay, or even this top section here, fluid sticks to the surface, and then what happens is it starts sticking here, and you have all this surface down here, and this red line grows. What is that red line? Well, that's the point where the velocity is 0 at the surface, and up to it, or after it, is free stream. Okay, so velocity above this red line is going at this velocity, whatever flow that is moving. Anything from the red down is going at the free stream down to 0. Okay, it's because the velocity sticks to the surface, we get a boundary layer, and because the surface is going to the right, it gets longer, that boundary layer grows. Okay. So you can figure out how thick that boundary layer is by that equation right there, the top one. That's for laminar flow. The bottom equation is for turbulent flow. Okay, in turbulent flow, if you remember from first fluids, it's kind of an erratic circulation. It's not nice and smooth and clear. Think about when you turn your faucet on. It's laminar first because you can see through it, nice and smooth. But once you crank it up, it becomes cloudy and it bounces around that turbulent. Okay. So these were just derived from experiments that someone did for their PhD. I mean, one PhD student probably derived that top equation and said, okay, that works. So everything is going to have a boundary layer, no matter what. As I'm walking here, I have a boundary layer sticks to my surface. But as I'm walking here, I have a lot of pressure drag, right? Because I have a lot of frontal area here. All right, if I turn here, I have less pressure drag. I have a little bit more surface drag. But as I'm walking, what's happening to the flow behind me? Yeah, we got a wake region because, yes, the flow sticks to my surface, but you can't make it bend back down because it's inertia. You can't. Same with you running down the hall trying to make a curve. It just doesn't want to make it bend, and therefore we get that wake region. Okay? And for laminar flow, the wake region's thicker. Okay? But for turbulent flow, it's smaller because you have more circulations back here that's helping grab some of the flow and helping it shrink down. So that's again why the golf ball with nipples creates turbulent flow, and you get these vortices circulations to help reduce the wake region. Okay. So I think I reviewed how to make this code for problem 1. All right. So I wanted you to find the boundary layer under new. So go ahead and use that. And let's give you a couple more equations here that you might need to know. Might as well just continue right here. Oh, might as well write it. 1/2 rho v squared CF times A. So write this down. I'll briefly talk about this. So if you're looking to find the friction, like surface drag friction, or say you're driving down and you see a UPS truck, they have 3 big sides, right, they're long or tractor trailers. If you want to find the friction on the top surface or the sides, use this equation. Okay? So these equations only give you friction along the surface, okay, like the sides of the truck. Okay. If you want to find the overall drag of the truck, you got to go back and use the 1/2 rho v squared CD. Okay. All right. So sometimes they just do that, and I'm gonna skip this. Say that again. Those are the L just is a subscript. Yep. So the Reynolds number is going to be rho VL over mu. So the subscript just defines, okay, that stands for length, right? The L? Yeah. No, length. Length. You remember how we had in the boundary layer? We had RE subscript X. The X just tells you that that's your dimension that you're going to plug in the Reynolds number. That's all. Yeah. So yeah, the L is just length. That's all that is. It's not specifically saying length. Okay. Yep. Good question. Talk about this later with the project. Okay, the last thing, and then I'll let you get back to work, or to work. So this is your fundamental equation to find the overall drag around an object. No, there's no difference. Nope, I can fix that for you. I didn't. Yep, I see what you mean. Nope, doesn't matter. Yep. So this just kind of tells you, this is kind of a weird shaped airfoil, but that's an airfoil. It has a length and like a depth or width or whatever. That's going to have both pressure and surface, or what they call friction drag. So you could call friction drag surface drag. Okay, they kind of call that interchangeable. So it's kind of weird. It's kind of that FF that I just showed you. Okay. And the total drag is you combine those two up. So that makes sense, right? If L is larger, much larger than D, you're going to have more surface drag. But if your diameter now gets bigger and the length gets smaller, your pressure drag is going to actually be higher. There's a point where there is minimum drag, right? Which is? Right there. Okay? Anytime you design something, you're going to design it so it's right there. Okay? Always. Because you don't want, well, I guess if you want high drag, like a parachute, right? But most of the time you want a lower drag. So you want to figure out where that graph would actually go. Okay? And maybe I'll try to have this so you can see how that works, how you can design that. I'll think of something to show you how to plot that. CD values are found right in your book. Let me get to the page here to show you. So page 619. They are chapter 11. And it's table 11.1, 11.2, 11.3. And they go through, if it's 2D shapes, here's 2D shapes, which a lot of times you do, and they actually go through the next few pages 3D shapes. Okay? So most of the time, things are 3D, right? A lot of the time you just use that. Okay? This gives you a close approximation. If it's 2D, but it doesn't really give you, it only gives you 2D effects, right? It doesn't have anything to do with the other third dimension. So that's why they give you those values. And you might have to look some of these values up when you do it. Okay? Maybe when you do the final, let's see here. When you do your numerical code, you can pick this right here, and you have Reynolds number and you have CD values. The turbulent, it actually changes to 0.2 all the time. Okay. Any questions regarding this? So you have the new homework that I posted. Quite a bit of stuff on there. So why don't you spend Thursday, right? Tuesday, working on that. Yep. So you come in here, go to the AC lab. If I have class in here, do that. Get caught up with it. Okay. There's another ANSYS on there that I want you to do. You can do Inventor, or you can do the actually another CFD that I want you to do on the computer. You can either do Inventor, there's tutorials, or you can do ANSYS. It's up to you. Okay. What I want with that is I want a total of 3. You've already done the first one. You only need to do 2 more. To do 3 tutorials by the end of the semester, I'm going to count that as an exam. Okay, it should be an easy exam. Okay. The reason why I just want you to get familiar with it and know how to do it. Say that again. A lot of companies are starting to use ANSYS, and actually a lot of companies are starting to want people that know how to do this CFD. Okay, because it's becoming more and more popular, and it's easier to get. Like Inventor didn't have it when I first started. It was just kind of crap. They only use ANSYS.
Oh, like Burnett said,
Now-
they steal a lot of things.
Now it's actually getting pretty good. And Chris has shown me some cool things that you can do with it that I didn't know you could do with it a few years ago.
I've got the rotation.
You got the rotation done?
The crash last time.
I was gonna say. It was,
So
it was
I
taking
crashed.
for,
I know the program.
it was taking forever, but it's possible, but.
No, ANSYS is free.
It's free.
And it was never free before. So that's nice. That's
Take
the version is
advantage.
free. Inventor now is free for you guys.
Only for free use.
If you're gonna take my, I'm gonna stop this. If, oh, come on.